This is my third video about materials. How big is an atom? You should be able to estimate now how big is an atom, and of course it's about 10 to the minus 10 meters. About 10 to the minus 10 meters. There's a couple of ways we can come up with. There's this calculation here. A mole of copper has a mass of 63.5 grams. The density of copper is that. Use that data to estimate the diameter of a copper atom. State any assumptions you make. Well, the calculation is basically saying that density is mass over volume. So volume is mass over density. So we can work out the volume of an atom. We know the mass of an atom is the molar mass divided by Avogadro's, and we know the density. And so we end up with 1.4 times 10 to the minus 10 meters. The assumption that we're making is if we assume that this atom takes up the space of this cube, then you've got lots and lots of cubes stacked on top of each other. Of course, it is just an assumption, and for various reasons it's not particularly accurate, but it does give us 10 to the minus 10. This is an experiment you should have done. It's called Raleighs oil drop experiment, and it's good for estimating the size of an oil molecule. You get a very thin wire, you dip it in oil, you use a magnifying glass, you get the diameter of the oil drop, then you put the oil drop on water, and it spreads out to form an oil slick, and you measure the diameter of the oil slick. And from that data, you can work out the size of an oil molecule. What we're basically saying is that the volume of the drop is equal to the volume of the oil slick. And so you can work out the thickness of the oil slick. Okay, an oil drop of diameter thingy. Have a go yourself. As I said, the volume equals volume. Here's the calculation now. Okay, the volume of the drop equals the volume of the slick. If I call the drop 4/3 pi r cubed, little r cubed, and then the volume of the slick pi r squared times t, where big R is the radius of the slick, then we get this expression. And if you bung in the numbers above, you get about 10 to the minus 9 meters for the size of a molecule. And we're of course making some assumptions about how the molecules arrange themselves in the slick. Something that must be talked about here is uncertainty. You know, what effect will the uncertainty, the biggest uncertainty is measuring the diameter of the drop, and you're never going to do that more than plus or minus 0.1 millimeters. So what effect will that have on our answer? What will be the uncertainty in the value of t? Well, looking at this equation I derived before, where t equals 4 little r cubed over 3 big R squared, just considering little r, if the uncertainty is 0.1, then the percentage uncertainty in little r is going to be plus or minus 20%. As we are cubing little r, the uncertainty in t as a result will be plus or minus 60%. And so that gives us an absolute uncertainty of plus or minus 0.6 times 10 to the minus 9 meters. The idea is, though, that it's just to get an order of magnitude, which it does so quite successfully. But there is a lot of uncertainty. And in this calculation, I'm ignoring the uncertainty in the value of big R. That will make it even more uncertain.